this is a joint work with Saket, Daniel and Meda. So let me start by introducing what is parameterized complexity, because in this talk we will be looking at guarding from the viewpoint of parameterized complexity, of course via CSPs. So parameterized complexity is one of the paradigms to cope with NP hardness. But rather than giving formal definitions related to parameterized complexity, I will give an analogy between classical complexity and parameterized complexity. So consider any classical problem Q. Here we are given an instance I, which is an instance of this problem Q. We can define a parameterized version of this problem, say we call it Q prime, which has the input I, and additionally it has an integer k, which is called as the parameter. So this integer k can be any structural property of the input or structural property of the output, or say solution size that we are looking for, or some interesting parameter which tells some more information about it. So in classical complexity theory, we usually measure the running time based on the size of the input. In particular, we measure in terms of the number of bits required to write the input. Whereas in parameterized complexity, we measure the running time based on the size of the input and the integer k. So here you may be wondering, like here k is also part of the input, then in the classical formulation, if k was part of the input, my running time would also depend on k. But notice that it will depend on log k, because we need log k many bits to write the integer k. Whereas here in parameterized complexity, we allow the dependence on k. So when I mention the running time, maybe it will be more clear. So typical goal in classical complexity is to design polynomial time algorithms for the problem. By that what we mean is polynomial in size of the input. Whereas the typical goal in parameterized complexity is to design an algorithm whose running time looks like f of k into polynomial in the input size. So here f is some computable function which depends only on this parameter k, hence the name parameterized complexity. So any parameterized problem which admits an algorithm with such a running time is said to be in FPT, and the algorithm is called an FPT algorithm for that problem. So as we all know, there are certain hard problems. Also, when we look at polynomial time solvables problems and the class P, we do not have polynomial time algorithms for all the problems that we need. Many times it turns out that we do not manage to design a polynomial time algorithm, and we have the notion of NP hardness, using which we give an evidence that problem is unlikely to admit any polynomial time algorithm. A similar notion is there in parameterized complexity as well. Not every parameterized problem can admit an FPT algorithm. So, and this hardness, the FPT kind of hardness is captured by the notion of W hardness. So here I am being a little loose. There is also an integer associated with this letter W. But for the purpose of this talk, what will matter to us is whether the problem is in FPT or is it not in FPT. So we'll not worry about that. So for us, we'll just worry about whether the problem given is FPT or not. Notice that for appropriate value of k, any NP hard problem is actually admits an FPT algorithm. In particular, if we look at the input size, any decidable problem will admit an FPT algorithm. So this is, but the goal in parameterized complexity is to choose a parameter which is smaller than the input size. So this is all that I have to speak about the parameterized complexity. Let us move to the problem that we are concerned with in this talk. The problem is called art gallery, and it is about guarding polygons. So before introducing the problems, let us introduce some notations that will be useful in understanding the problem definition. So whenever I say a polygon, I will mean it will be specified by a sequence of points in the plane where two consecutive points have the line segment between them, which will be part of the boundary of the polygon. So these consecutive edges, line segments will be called as the edges of the polygon, and the points using which we specify the polygon are its vertices. We will assume that if you look at any two edges of this polygon, they are not self-intersecting. By that I mean except at the endpoints. Of course, look at the point, look at the vertex at which it has the two of its edges. Then at this point, these two edges intersect. But apart from that, there are no intersections. Secondly, we'll assume that the polygon does not have holes. By that, what I mean is, if you remove the boundary of this polygon, then the plane will have exactly two connected regions. It cannot happen that there is a hole in between. For instance, so if we have a polygon like this and we have something like this, then this will be a hole. Because if I remove the edges of this polygon, I will get this region, and this region. So I'll get more than two. So this won't happen with the polygons that we are considering. So let us define the notion of visibility inside a polygon. So consider 2 points S and T inside this polygon. We say that points S and T see each other if the line segment between S and T is completely contained in the polygon. Whenever I say a line segment is completely contained in a polygon, I include the boundary points as well as the vertices. So also these points S and T can be on the boundary of the polygon or one of the vertices, or can be strictly. So in this example, the point S sees the point T, whereas the point S does not see the point Q, because if you look at the line segment S and Q, there is this portion of the line segment which is not contained in this polygon. Therefore, S does not see. So let's fix one more notation. So a vertex in a polygon is called as a reflex vertex if its interior angle is strictly greater than 180 degrees. For example, this vertex U is a reflex vertex. And we say that a vertex is a convex vertex if the angle is at most 180 degrees. And here is an example. If you look at vertex V, the interior angle is at most 180 degrees. So it is a convex vertex. So now we are ready to define our problem. So the art gallery problem takes as input a polygon P and an integer K. And what is the question? The question is whether we can place K guards in P, in points of P, so that we end up seeing the whole points in P, all the points of P. That is, we guard all the points of P. For example, if you place two guards here in yellow box and pink box, the pink region shows the visibility region of this guard, whereas the yellow region shows the visibility of this guard, then you will notice that we will end up guarding all the points in this polygon. So if the integer K that is part of the input, if it is greater than or equal to 2, we can always say that it's a yes instance, because here is a solution. That two guards are always enough to guard this problem. So there are different versions of this problem defined in the literature, and all of them are quite well studied. These are based on where we are allowed to place guards and what all points do we need to guard. So this leads us to the notion of XY art gallery problem, where X is the set of points where we are allowed to place the guards, whereas Y is the set of points which we want to guard. So typical examples of these sets X and Y are the vertex set of this polygon, or the boundary of the polygon, or all the points in the polygon. So based on what X and Y are, we get different versions of the problem. So and the input is again for the XY art gallery. We have a polygon, we have an integer K, and the question is whether we can place K guards in the points that are in X, and we want to guard the points of Y rather than guarding the whole. So in the classical setting, the first problem that was defined, in that X and Y both were all the points of P, and that was the example that we saw on the previous slide.
So in this example, one guard is not enough, because there's a reflex, when the reflex.
Sometimes it can be still enough because if there is just one reflex vertex, it can guard it. So, here two are necessary. Yeah.
So can we say that if if the guards are guarding all the vertices, then the whole region is guarded?
No.
It's not.
No. We can actually come up with examples where this is not. And even if we guard the whole of boundary, then also it is not. Yeah. So let us look at some of the known results. Although there are a lot of results, we'll just look at some of these results. So this problem was posed back in 1973, and the first problem that was posed was a combinatorial question which asked how many guards are always sufficient to guard a polygon on n vertices. So in this talk we are looking at polygons without points. Okay. So it was proved in 1975 that n by 3 guards are always sufficient, where n is the number of vertices in this polygon, and also they are sometimes necessary. So there are polygons in which you need n by 3 guards. So this combinatorial question was answered in 1975, and later, sometime later, the point art gallery problem was shown to be NP hard when the polygon contained holes. So here in this construction, the holes could not be avoided. The holes were necessary. And here the point version is where we want to place the guards. We can place the guards anywhere in the polygon, and we want to guard whole of the polygon, including the interior. So, but this NP hardness result was improved, and it was shown that vertex point art gallery is also NP hard. That is, we want to place guards on the vertices and we want to guard whole of the polygon. Then also the problem is NP hard, and here the polygons did not contain holes. So this is for polygons, simple polygons. And this result also extends to various versions of vertex art, various versions of art gallery, and this actually all this NP hardness results also show that there is no sub-exponential algorithm for this problem. That is, there is no 2 to the little o of n algorithm for this problem where n is the number of vertices in the polygon. This is under the assumption that exponential time hypothesis is true. So, much later, an order log of approximation was obtained for the boundary point art gallery problem. There are many known approximation algorithms for various restricted settings, but solving it in full generality without any restriction on the input, this log opt approximation was obtained only in 2011. In 2017, point art gallery was shown to admit an ordered log opt approximation algorithm, but here there is some assumption on the input. In particular, they assume that the coordinates of the points that appear as vertices in the polygon are integers. Also, they assume some general position assumption. So, and this is necessary for them because they convert, given the polygon, they create some grid inside this polygon, and they are looking for guards which are from the grid points, which gives them the desired approximation ratio, but it does not work when the coordinates are not integers or the general position assumption is not. So let us look at some exact algorithms for this problem. Recall that I mentioned n by 3 guards are always sufficient to guard any polygon on n vertices. So it turns out that actually we can find such a solution which uses at most n by 3 guards in linear time. So this was quite old result. But when we come to the optimization version of the problem, where we want to optimize the solution size or we want to test if k guards are always enough, then this problem was open for quite long time. Whether, especially the point art gallery version, there was no known exact algorithm for this problem until 2006. So the problem was defined in 1973, and for the point version, the first exact algorithm was found only in 2006. And this exact algorithm actually converts the polygon, the instance, to to solving some set of polynomial equations, and that is the only method we know. This uses this heavy machinery of solving this polynomials, and we know no other simple algorithm. So, and this was the first exact algorithm. It was not even clear before this result whether point art gallery admits any algorithm.
So what is K?
K is the number of cards. So let us look at one of the relevant results from the realm of parameterized complexity. So in 2016, it was shown that the art gallery problem parameterized by the solution size, which is the number of guards, is double one. So which means that this problem does not admit any FPT algorithm when parameterized by the number of guards. So and this, when I say here I am just saying art gallery, this result holds for all the versions that I mentioned. Like where x and y, the sets x and y are either points, boundary or vertices. For all combinations of these, the result holds. So for all these things, we know that the problem does not admit any FPT.
These different versions are compatible. I mean, does the complexity, does the hardness of one of them imply the hardness of
And for example, if you look at vertex art gallery, it has N-choose and Y3 exact algorithm, which was known long time back, right? It's just enumeration, but point art gallery we didn't know anything till 2006. So inspired by the above result, Giannopoulos posed an open problem whether this problem admits an FPT algorithm when parameterized by the number of reflex vertices. Recall that reflex vertices are those vertices which have interior angles strictly greater than 1. Those are reflex vertices. So right, so somebody posed this problem, but why all of a sudden reflex vertices? Yes, we know that the problem does not has an FPT algorithm parameterized by the number of guards, but why do all of a sudden we choose the number of reflex vertices as our next parameter? So I'll explain it in the next slide. So it turns out that if you place one guard at each of the reflex vertices, then you will end up guarding the whole polygon. And this holds for any polygon without holes. Just place one guards at reflex vertices and you're done. You'll end up guarding the whole polygon. So what does this mean? So if the input integer k, which is the number of guards we are looking for, if that is greater than or equal to the number of reflex vertices, then we can trivially say that the instance is a yes instance. Otherwise, the number of guards that we are looking for is upper bounded by the number of reflex vertices. So this is why, because this number is maybe larger than the solution and upper bounds the solution size, this is the next natural choice of the parameter. Yes. So actually you place guard at any vertex or anywhere in the polygon, it will guard it. It's a convex. So now let us look at what results we have. So we show that we start with this problem called vertex art gallery, where we want to place the guards on the vertices of the polygon and we want to guard only the vertices of the polygon. So both x and y are vertices of the polygon. So it turns out that after gathering enough structural insights into the solution, we can convert it to some structured instance of this vertex art gallery version, and once we have gathered the structural insights into the solution, we can write a special kind of CSP for this problem. CSP stands for constraint satisfaction problem. I'll explain it later. So, and we also designed a polynomial time algorithm for this special kind of CSPs. So, once we gather this insights, we create. So, whenever I use R, I will mean the number of reflex vertices in the input polygon. So, after gathering the structural insights into the solution, we create some function of R many instances. Here it is R to the order R square many instances, and each such structured instance can be solved using a CSP. So, given this instance, we can convert it to an instance of the special type of CSP, and for which we design a polynomial network. So thus we obtain that if you look at the vertex art gallery problem, then this is a fixed parameter tractable when parameterized by the number of vertices. So it turns out that when we look at vertex boundary art gallery, we can convert it to an almost vertex art gallery kind of problem. Here I'll explain what I mean by almost briefly, and this we can do by discretization. So what do I mean by discretization? So given the polygon, I can subdivide its edges possibly multiple times so that guarding this newly added vertices together with the vertex of the polygon is enough to guard the whole boundary of the polygon. So this we can achieve by discretization, by subdividing edges appropriately. Here we need to know how to do it appropriately so that guarding these vertices together with the fake vertices that we add ends up guarding the whole boundary. But this does not give us vertex art gallery problem directly because we have introduced fake vertices. So vertices which were not originally part of the polygon, but we added it for our convenience. And we are not allowed to place guards on the fake vertices. So we have to be a little careful so that we avoid placing guards at this fake vertices. But it turns out that even this almost version of this vertex art gallery can be converted to a more structured form of the problem by again gathering structural insights into the solution, again with r to the order r square many instances. And for this structured form of instance also, we can write a special CSP and solve it in polynomial. So this CSP is the same as the previous special CSP. So thus we obtain that even the vertex boundary art gallery is FPT when parameterized by R. The same can be done for the case when it is boundary vertex art gallery. Again we discretize it and we show that if we subdivide the edges to create more vertices, these fake vertices, and we can show that if there is a solution, then there always exists a solution where the guards are placed only in the vertices of the polygon or the fake vertices of the polygon. So and again by converting it to structured form of the problem, again we write CSP and solve it, thus obtaining the FPT algorithm. So it turns out that boundary art gallery is much more tricky. The discretization trick that I was describing in the previous two slides do not work here. So we cannot discretize it and obtain something. But it turns out that even boundary art gallery can be converted into the structured form of instances for which we can write very structured CSP, but this CSP is not the same CSP as the previous type of CSP. And currently we do not know whether this CSP can be solved in polynomial. Notice that here we have created r to the order r square many instances, and when we are writing this CSP for a structured instance, it turns out that the number of variables we add is function of r unknown. So even if we design an FPT algorithm for the special CSP, when parameterized by the number of variables, then we will be good, because we are only interested in designing FPT algorithm. So we do not even know if this problem is fixed parameter tractable when parameterized by the number of variables that appear in this space. Domain is unbounded. It has size n, which is the number of vertices. So it's just that the number of variables is. So thus, although we can convert it to the structured form, we do not know at this point whether it is FPT. So since I mentioned constraint satisfaction a lot, because that is what we use in our algorithm at the end, so let us fix this. So let us understand what CSPs are. So constraint satisfaction problems are a prototype problem, and its full generality it looks like this. So it has a finite set of variables, say x1, x2 up to xn, and for each variable we have a domain d1, d2 up to dn. So these domains need not be finite. They may not be even explicitly given. say for instance, one of the domains could be the set of natural numbers or real numbers or any finite or infinite set. They can be any and they may not be explicitly specified. This is the variable set and domains, and then we have constraints over the variables. So how does a constraint look like? So a constraint has is an ordered couple of variables. So here choose a subset of variables and then you have an ordering on them. And then there is an allowed set of values for this tuple of variables. For instance, this constraint C1 has three variables x, y, and z. And as a tuple, they are allowed values only 1, 3, 2, 5, 2, 6, and 2, 1, 1. So we say that when we assign values to the variables, the constraint is satisfied if and only look at the tuple of values that we get. This tuple of values must belong to the allowed set of values. Then we say that a constraint is satisfied for that assignment for the variables. So, and this allowed set of values may not be explicitly given. For example, a constraint can look like x plus 5y equals to 0. So here we are not, here there can be infinitely many values which satisfy this constraint, but we do not list all of them exhaustively. We can just mention it as some equation or some inequality. So, and what is the question here? The question is whether we can find an assignment. For each variable, we can assign a value to its domain so that all the constraints can be satisfied. So this is the goal of the constraint satisfaction. So unfortunately, it turns out that CSPs, when parameterized by the number of variables, it is W bar. So let us see, so this is a folklore result, but to understand CSPs more, let us see why this problem is W bar parameterized by the number of variables. So this reduction goes from multicolored click, which is a paradigmatic, which is a very well-known W bar problem in parameterized complexity. So here the input is a graph G, and we have a partition of the vertex, which is V1, V2 up to Vk, as it is shown here in the figure. And the question is there a click in this graph which contains one vertex from each of the parts? So this instance is a yes instance because if you look at the red edges, you can see that it's a click which selects exactly one vertex from each of the parts. So this problem is W1 hard when parameterized by the number of parts, which is K. So this we will use as a source problem for our reduction. Let us see how the reduction goes. So what we do is, we will create a variable for each element that appears in our solution. So what is our solution in this case? It is a set of vertices and the set of edges between them. So which satisfies certain condition. In this case, it is the condition that together they should form a click. So what do we do is, so for every part Vi, we create a variable xi which will correspond to the vertex that we select from part I. Okay. And the domain for this variable will be Vi, which is the part for which this variable is created. So for every distinct I less than j, we want to select an edge between the part Vi and part Vj. So this is why we add a variable denoted by Eij, which will correspond to the S that we select between part I and part j. So here the domain for this variable will be the edges between Vi. If U is the endpoint from Vi, part Vi, then we want that this vertex selected should be same as this vertex U. This is why what constraint we will add is, for every I less than j, we want that variable selected from xi should be the lower endpoint of the edge Eij. So here, what is this function flow? This takes an edge and returns the lower index of the vertex. So suppose it is between part Vi and Vj, I is the lower index part, so it will return that particular vertex. So this is what flow is. Similarly, we can do for the higher endpoint and add the constraint that Sj should be equal to the higher endpoint of this edge Eij, and that is it. Now, because we created only k plus k choose too many constraints, k plus k choose too many variables, what we have is the number of variables here. The number of variables here is some function of k. So if this problem, this CSP admitted in FPT algorithm parameterized by the number of variables, we can obtain an FPT algorithm for multiple variables. So thus this cannot happen under the assumption that this is W hard. So we obtain that. Indeed, this problem is W.
So that k is 2 into how many constants are there?
Constraints are 2k choose 2.
2 cases.
Right. Yes. So even if you parameterize by the number of variables plus constraints, still it is okay. Because here the domain sizes are not bounded. They are as large as n choose 2. Yes, exactly. Yes. Domain and the number of variables. Yes. So I talked about special type of CSPs when I was describing the results that we have. So let us look at what that special CSP is. So if you remember from the last slide, and the constraints, the type of constraint that we added, it involved only 2 variables. But the functions were arbitrary. So here we will see that we have some structure over the functions. So what is monotone 2 CSP? Here again we have some variables, finite set of variables x1 to xn, and we will assume that all of them have same domain and finite domain, and we have some constraints. So the constraints involve only two variables, and also constraints. All the constraints are of the following form. It is either some variable x greater than equal to f of y for some variable y, or it is x less than equal to some f of y. So here note that again, if you look at the arity of the constraints, which is the number of variable appearing in it, it is 2. In the previous slide, you saw that the CSP which involved 2 variables in its constraint is W bar. So we need more condition. Okay. So what do we do is, what we need is this function f must either be non-decreasing or non-increasing. So this is why the word monotone comes in the name of the problem, that the functions are monotone, and this 2 comes from the arity of the constraints appearing in the constraints of the CSP. So this is why the problem is called CSP. And again, we are looking for an assignment where each variable is assigned a value from the domain, so that all the constraints are satisfied. This, for simplicity, we will assume we can do something if the domains are. So as I mentioned earlier, this problem is polynomial times 1. Let us look at how we obtain such an algorithm. So the algorithm is not that complicated. We obtain the algorithm for monotone 2 CSP by reducing it to 2-SAT. And 2-SAT is a paradigmatic polynomial time solvable problem. So once we obtain this polynomial time reduction, we can use the 2-SAT algorithm to solve it. So let us look at the variable set in our 2-SAT instance. So here note that we have variables in the CSP and variables for our 2-SAT instance. So here I am describing the variables that will appear in our 2-SAT instance. So for each variable x that appears in our CSP instance, and for each value from 0 to n plus, here we will assume that the domain is 0 to n for simplicity. Otherwise, we can just, because the domains are finite, we can fix a mapping from the size of the domain to this. Okay, so we will assume that d is 0 to n, and for each value d, which is from 0 to n plus 1, we will create a variable for our 2-SAT instance, which will be denoted by xt. So we have each variable x for a and each value d from 0 to n plus 1, we have this variable xt. So how do we interpret this variable that we have in our 2-SAT instance? So whenever the variable xt in the 2-SAT instance is set to 1, we will interpret that in the CSP instance, this variable is set to a value which is at least. That is, x should be greater than equal to. This will be our interpretation. So this is all the variables that we create. Now let us look at the constraints the clauses that we add in our two-sided channels. So before encoding the constraints of the our CSP, let us add some clauses that will ensure some kind of sanity check. That is, the first thing we need is that a variable must be assigned a value from 0 to n plus 1. So notice that if all the variables are set to 0, so if consider a variable x, and for every value d, xd is set to 0, you don't know how to interpret this. So this is why we will want that x must for each variable x, it should get a value which is at least 0 and less than equal to n when it is less than 0. So this is why what we do is we add the clause x0. So this is a clause which comprises of just one variable in the positive form. So this must always be set to true. Similarly, we add the clause not of xn plus 1 so that a variable can never be set to value n plus 1 for a yes instance. Okay. So this was for ensuring that a variable is assigned a value from this domain. Let us do one more thing to ensure some kind of consistency. So notice that if look at any variable x in the CSP, if it is assigned a value say 3 from the domain, 3 appears in the domain, then x greater than equal to x greater than equal to 3 is satisfied. But also x greater than equal to 2 is satisfied. Also x greater than equal to 1 is satisfied. So for our reduction to work, we need this information to be encoded. So to do this, what we do is whenever xd is set to 1, that is whenever x is set to a value which is at least d, we want the condition to be satisfied that xd minus 1 is also true. That is, x is also greater than equal to d minus 1. This is why we add this clause. Notice that this we do not need to do for every pair of value d comma d prime where d prime is less than d, because this will form an implication chain which will force it. So doing this much is enough. So now let us see how we encode the constraints. So recall that in our monotone 2 CSP, each of the constraint was of the form a variable x, there was a sign which was either less than equal to or greater than equal to, and some function of a variable y, where this function f was either non-decreasing or non-increasing. So let us consider the case when the variable x is greater than equal to f of y, where x and y are some variables, and f is a non-decreasing function. So here, what do we want to do? So whenever the variable y is assigned a value which is at least d, we want that x must be assigned a value which is at least f of d from this constraint. So this is why we add the clause that whenever yd is set to 1, then we must set x f of d to 1. So this is encoding. Okay. So this was one example where the sign was greater than equal to and the function f was non-decreasing. But believe me, for all possible signs and functions, we can obtain clauses similarly. They will not look like exactly the same, but they will involve just two variables. And we can
So both the clauses are added for all.
yes, for all. Okay. So then we can show that the instance of monotone 2 CSP that we started with and the 2 start instance that we created, they are equivalent instances. And hence we have reduced our problem to 2 start, and now we can employ the algorithm of 2 start to solve the problem. So this is why the problem is okay. So now we are done with the CSP. We know what special kind of CSPs are we using, and we have also seen how do we solve that CSP. So now let us move back to our FPT algorithm, which is FPT algorithm for the art gallery problems parameterized by the number of vertex vertices. So here whenever I mention art gallery, unless I specify the x and y sets, I will always mean vertex art gallery. So we want to place guards on the vertices and we want to guard the vertices. For the rest of the talk, we will use our gallery for that version of the talk. So before proceeding with the algorithm, let us fix some notations. So whenever we are given the polygon as the input, we will label them from 1 to n, where n is the number of vertices of this polygon. So in the order in which the points are specified. So here we have n equals to 11, so we have labeled the vertices from 1 to 11 in the side. So let us define what we mean by convex region. So whenever I highlight any vertex with this red circle, these will be reflex vertices. And what we mean by a convex region is a region which is between two consecutive reflex vertices. For example, 5 and 1 are consecutive reflex vertices. That is, we do not have, if you go from 1 to 5, there is no reflex vertex in between. So this will, the vertices strictly in between will comprise a convex region. So whenever I say convex region, we do not include this and convex. So it only comprises of convex vertices. So if you look at a convex region, it is a set of maximal consecutive convex vertices in the polygon. So this is what we mean by convex regions in the polygon.
Excuse me, ma'am. Can you please go to the previous slide? Does it mean that suppose 5 and 9 are consecutive reflex vertices? So if I join 5 and 9 and then I shade the region that's to the right of it, that must be a convex set. Is it what it means?
No, that's not it. So here also it's not good, right?
In this example, it's not.
Yeah.
So
So
this
it may not
convex is different.
Yes. Okay. But we will always exclude the reflex vertices. This will be very crucial in our group. Okay. So whenever I say convex region, it will only include convex vertices. It will never include the endpoints. So if you look at this yellow region, this comprises of this yellow vertices. So this vertex 2, 3, 4 will comprise of a convex region in this polygon. But we cannot include this vertex 5.
So region means a set of vertices
Yes.
or a shaded?
It's a set of vertices because we are interested only guarding vertices and placing guards on the vertices. So the way we define convex region is by the vertex. It's a sequence of vertices and a maximal sequence whose endpoints are not reflex vertices. So all the
I guess the reason inclusion in the name can be possibly that it's enough to put in one card in each of the convex regions.
yes, that is always enough, but the optimum solution size can be much smaller. Yes, exactly. Yes. So this will give us much handle on this. So okay. So okay, let us look at. What we wanted to do is we wanted to convert the vertex art gallery to some structured version of the problem. So let's see what we mean by the structured vertex art gallery. So here we have the polygon P and we have the integer k as the input. Apart from that, we have the following functions. So these functions will give us some structural insights into the solution. So let us understand these functions via an example rather than reading them. So what these functions hash GP tells us? It tells us for each convex region and reflex vertices, how many guards do I want to place there? So for example, here hash GPCA is 3. So I want my solution to place exactly 3 guards in CA. Here it is 1, so I want to place 1 guard. Here it is 2, so I want my solution to place exactly 2 guards in this convex region. So now let us look at what we mean by hash GS. Hash GS is the number of guards required to see a convex region. So here hash GS of this convex region CI is 4. So in the solution that we are looking for, we must require 4 guards that see this region. This guard may be placed here or somewhere else. But we will want that this convex region is guarded by 4 guards. So and it is necessary that 4 guards guard it completely, and they are also we require 4 guards in order to guard it completely. So let us see what is the purpose of this house CI. Okay, so this hash CI gives us division into the visibility regions into consecutive sub-regions of the convex region. So here, since hash GSCI is 4, we want 4 guards to see this, and this must be consecutive to this. Okay? So now let's see what is the purpose of function house here. This we will have for every convex region. So this exactly tells us how this region must be seen. So this is a function from the number of guards required to see it. So there is 1, 2 up to hash GSCI to which guard and which is the guard number which sees this region. So let us forget this and look at an example.
So I think understand visibility detail. Meaning that the fourth guard should not be able to see the third region.
It can see.
It can see.
Yes, it can see. But what we want is
It must be able to see the fourth.
yes. So whom we are charging the visibility. That is important. Okay. So let's see this with an example. So suppose how the first region of convex region CI is given by the pair CA, 2. This means that look at this region and look at the second guard placed in this region. So here squares denote the guards placed. So look at the second guard which is placed in this region CA. This guard must see the first region. So a priori we do not know how these regions are divided. We just know that they must be consecutive and we'll be encoding it somehow. But we want that the second guard placed in this region must guard the first region. So this must see all the vertices that belong to the first region. Similarly, if how the second region of convex region CI is seen as U, 1, then the guard placed at vertex U must see the second region. So similarly, if how the third region is seen is given by the pair CA, 3, then the third guard placed at convex region CA must see the third region, and so on. So this is the purpose of these functions. Okay? So how do we go from the art gallery to structured art gallery? And here I only mean vertex version. So just guess these functions. Notice that. Look at how many distinct functions hash GP are there. K is upper bounded by R by our previous argument. So the number of functions hash GP is bounded by R to the order R. Similarly, the number of function hash GS is bounded by R to the order R. And so let us look at this function. So this is here we can have something like R square order R square many tuples. Okay, the size of this set, and this is at most k because we are placing at most k guards, right? So this value is at most k. So the number of such functions is R to the order R. But the point is, we want to guess it for every convex region, and there are order R such convex region. So the number of guesses we need is R to the order R. So once we guess this, we can obtain a theoretical reduction and show that the original instance is a yes instance of the art gallery, even only if there exists some instance of the structured version which is a yes instance, and hence we are done. So we have converted our art gallery instance to a structured art gallery instance. This reduction is true. Okay, so we are done with this part. We have created R to the order R square instances. Now let us look at how we go from structured vertex art gallery to the special CSP. And here the special CSP will be the monotone 2 CSP that we talked about. So before that, let us introduce some functions which will be useful. Consider a convex region, say Ci, and consider convex region Ci and a point P in this convex region, and consider some other convex region Cj. We say by the function first P, Cj, we denote the lowest index vertex that this vertex P sees in the convex region Cj. So let us look at this example. Look at this vertex P. Here it is 7. Then P does not see 10. P does not see 11. But P sees 12. P also sees 13. But the point is, the 12 is smaller than 13. So the lowest index vertex that this vertex P sees in this convex region Cj is 12. So first of 7, Cj is 12. Okay. So this is how we define first of P, Cj for a point P and convex region Cj. So So we can analogously define the notion of last seen vertex, where instead of this lowest index, we will have the highest index. So now, let's see, there is a notion of continuity in visibility. By that what I mean is, consider any vertex P and a convex region Cj. Look at the first vertex that it sees in this region and look at the last vertex that it sees in this region. We can argue that this vertex sees all the vertices that appear here. So we can actually define the polygon Q with this vertex Q and the convex vertices in this region and show that this Q is a sub-polygon of P, and it is also, we can argue that if we place a guard at P, it sees everybody, and obtain that P sees all the vertices appearing between first and last vertex. Okay? So this continuity will be very important for us. So the second important property will be the monotonic property of how a convex region sees another convex region. So let us consider two convex regions Ci and Cj. When we are moving from one endpoint to the other endpoint in this convex region, the way the visibility is moving, this function will be monotonic. Let us understand this by an example. So for example, look at this. So this occurs only after we remove occurrences of nil, when we assign first of some vertex from a convex region to nil if it does not see anything. For example, look at this vertex 5. It does not see anything in this convex region. So we put for the first vertex that 5 sees in Cj is nil. Okay. Let us look at vertex 6. The first thing that 6 sees is 11. So first of 6 comma Cj is 11. First of 7 comma Cj is 12. Then first of 8 comma Cj is 13. Also first of 9 comma Cj is 13. So if you look at this function, that this numbers that you obtain, you can show that this will either be monotonically non-decreasing or monotonically non-increasing. Okay. So this is so when we talk about visibility, we can always show that this function first p comma Cj and also last p comma Cj, they're either monotonically non-increasing or monotonically non-decreasing. Okay. So now let's see how we go from structured version of art gallery to the monotone to CSP. So let's see what are the variables here. So recall that we had this function which tells us how many guards we want to place at a convex region of a reflex vertex. So we create one variable corresponding to each such guard. So suppose we want to place hash GPC many guards in convex region C. So there are hash GPC many guards in the convex region. So this variable xc, 1 corresponds to the first guard that we want to place in C. X2 corresponds to xc, 2 corresponds to the second guard that we want to place in this convex region, and so on. So now this was the variable set. Now let us look at the constraints that we have. So recall that we had this function hash gs, which tells us how many guards are required to see this convex region. In this case it is 4. And also we have functions which tells us which guard is responsible to see which region. So suppose how of Ci of 1 is Ca, 2, then the second guard that we placed here must see the first region. So which means that it must see the first vertex in this convex region. This is why we add the constraint that first xca, 2, ci, that this vertex in the first thing that this vertex sees in ci must be put 5. So now it will see some portion, and after that we want the second guard to be seen, who is responsible to see this region. So here suppose how ci, 2 is u, 1, that is the second region must be seen by the first guard placed at u. Then we want that, look at this vertex A. This guard must see from vertex A onwards. This is why the first vertex that this vertex sees in this region must start before or at A. This is why we have this constraint that first of xu, 1 in ci is at most the last vertex that this guard saw, the previous guard saw, plus 1. Because if its first is even 8, we are fine. We also want that if this vertex A sees 6 and only 7, we don't want it to end at 7. We want that the last should go till 8 or beyond. This is why we add this condition for last as well. So this is how we proceed. And then once we reach the last guard number which is responsible to see this convex region, we need that this guard must also see the last vertex of this convex region. Therefore, we add this additional constraint that this should be the last vertex of this convex region. So now once we have these functions, recall that we argued in our previous slide that functions first and last are monotone. Either they are non-decreasing or non-increasing. Once we delete the occurrences of nil, and we can delete and create our functions appropriately, then these are monotone functions, and it is not very difficult to see that sum of two monotone functions or difference of two monotone functions are also monotone, and we can obtain that all the functions are monotone this way, and now we can employ our CSP, the monotone to CSP. So this we can solve it in polygon. Okay, so to conclude, we showed that all these versions, vertex, art gallery, vertex, boundary, art gallery, and boundary, vertex, art gallery, are FPT when parameterized by the number of vertex vertices. And we have actually found some more applications of this monotone to CSP for which we designed polynomial time algorithm, but I will refrain from stating those because we have not yet typed. So, and we believe that this can have wider applicability. So, the version that is remaining is when what about all other versions that we did not talk about? So, one such version is point art gallery, where we want to guard whole of the polygon and we can place guards anywhere. Is this problem FPT when parameterized by the number of reflex vertices? For that matter, even if one of x or y is the point set, we do not know anything. Yes, we do not know that also, because we at the end do not know how to solve the CSP, but here we do not know anything what to do, how to proceed. So there are also different interesting computational geometric problems. One closely related such problem is terrain guarding, which you can imagine that on the plane you have this terrain, you have this vertices like small mountains and which are connected by edges here, and we want to guard the whole of the top side of the terrain where 2 points are visible. If you look at the line segment, that is completely contained above. So this looks like the art gallery problem, but it is not that much like an art gallery problem. So for this problem, we managed to design a polynomial kernel when parameterized by the number of reflex vertices, and but this was parameterized by the number of reflex vertices, but we do not know if this problem is FPT or not when parameterized by the solution size. So the arguments for the art gallery do not extend. Thank you.